In the last video, I've talked about how you can use your left hand to determine the direction of the magnetic force acting on a wire that carries a current, if you know the direction of the current and magnetic field. And you do it by associating your thumb with the force, first finger with the magnetic field direction, and middle finger with the current. Now be careful. I've seen some students who, instead of pointing their first finger in the forward direction, they would point the middle finger in the forward direction and point the first finger at an angle. That would be wrong. The first finger must always be in the forward direction, with the middle finger in the perpendicular direction. Now I'm now going to look at this in more detail. I'm going to look at how a formula that would allow us to calculate the strength of the force as well, if we know the strength of the current and the magnetic field. Now, in order to do this, the formula is one that we can only use if we have a uniform magnetic field. So only in that ideal case. Let me try and draw a uniform field. Okay. Now, typically, a magnetic field would have lots of curved lines coming out from the north pole of the magnet or going into the south pole. So if I want to have uniform field, now if you look at this magnetic field again, you see that there are lots of curved lines, and it really doesn't. Well, we would think of a uniform field as we've seen in, say, the gravitational field near the ground, near the surface of the Earth, or an electric field between parallel plates. So in a uniform field, as we have seen, the field lines should be parallel to each other. Now, if you look at this picture, the field lines get all spread out, but there is a place where they are a little bit parallel. That is when they are very close to the north pole of the magnet. Right? This bit here, just after they come out, or after the lines come out of the north pole, they are roughly parallel. But soon after that, they would start spreading out. Okay, so there is a way to have a more uniform field in this region, and that is to use a bigger, a larger or broader north pole, meaning that I should really have a fatter, thicker magnet. So let me try and draw this. Okay. Now suppose that I have a really big magnet that can cover the whole of the length of this iron rod. Okay, so I have this really huge magnet, really broad. It is possible to get such a magnet that has a really wide face for the North Pole, but it doesn't have to be really huge in the sense that it can be quite short. It can be quite short. Perhaps it's only this. Only this, right? Without those bits. So, and it helps if we also have a south pole beneath it. But for now, I shan't go into that. So let's say that this face of the magnet is the north pole, and I'm just going to assume that it is that we can actually set this up, and we have fairly uniform field. We have fairly uniform field coming down over the iron rod. Right. So for now, that's mainly what I'm interested in. I'm mainly interested in the region around the iron rod because I like to have I want to look at the formula that we can only use to calculate the force when the field is uniform. So and I'm really only interested in the field on the iron rod. So I don't really have to worry about the field elsewhere. So further away from the iron rod, if the field gets more curved as it spreads out, that is okay for now. Okay, so that's the magnetic field. So at least in this part here, this region here around the iron rod, I have a roughly uniform magnetic field. Okay, so we can work with that in practice. Okay, now right, so I shall represent the magnetic field, the strength of the magnetic field by the symbol B. I would represent, say, the currents. The currents would be going in this direction. I would represent the currents by I, by the letter I. And as we have seen, there would be a force in that direction. There would be a force, that magnetic force that pushes the currents in that direction. I'll call it F. Now, I would like to talk a little bit more about the nature of this force. This force does not just act on one point of the wire. It acts on every point where there is current and magnetic field. So if I pick any other point, let's say that point on the wire, as long as there's current there and there is magnetic field there, it would experience a force. And any other point, really, like that point. So in this case, since I'm setting up a uniform field that covers the whole iron rod, and since I know that there's a current going through the length of the iron rod, so therefore the full length of the iron rod, except maybe the two ends here, except this end and that end, which there's no current flowing through. So the part where there's current flowing through, right, all of the part where there's current flowing through would experience a force because all of that current is covered by the uniform magnetic field. And I also like to give a symbol to the length of this piece of iron rod, to the length of the part that has current. I shall call that L. Okay. Put the L there. I shall call that L, little L. Okay. So, okay, we have a fairly complete description of the situation. Now let's think about the formula. The formula relating the force to the current, the length, and the field is given by F, the force, is equal to B I L. The magnetic force is equal to the strength of the magnetic field times the current through the wire times the length of the wire. Right, be careful about the length bit. It's just the bit of the length that has current flowing through, not including the these two N bits if there's no current there. Right, the current will just skip from, say, this part of the rod into the copper wire that goes to the battery. There will be no current on the outside bits. So this is the formula. Now if you look at the formula, let's look at the formula and think about it a little bit. If you look at this formula, it's simply, we just simply have to multiply the three quantities together: the magnetic field strength, the current, and the length. And what this suggests is that if I have a, say, bigger, stronger magnetic field, if I use a stronger magnet, then the force should be bigger. That makes sense if if there is no magnetic field, if there's no magnet, for instance, B would be 0, and therefore there's no force. Okay, so we only have force when there is a magnetic field. So it makes sense that if the magnetic field is stronger, the force will be stronger. The current I. If I have if I have no current, then there would be no force. The force only comes from the combination of magnetic field acting on the current. So no current if I is 0, F is 0. That's what we would expect. And if the I is bigger, the force is bigger. So again, that seems to make sense. How about the L? As I've described just now, the force acts on every bit of the current or of the wire where there is current. And the same for each bit of the wire. Well, bit is a bit vague. Let's say for every centimeter of the wire where there's current, the same force would act. So therefore, if I have a longer wire with currents, then there would be more centimeters and therefore more force acting. So the overall, the combined force would therefore be bigger if the length is greater. So that makes sense also. If I have a longer wire with the same current and with, of course, magnetic field over the full region, the full length, then the force would be stronger. So, but although it makes sense that when each of these quantities is bigger, we have a bigger force, it doesn't, this description doesn't really confirm that this is the correct formula, because, for example, why can't we have B squared IL or BIL squared or some other power or even some other numbers multiplied by it? So I shouldn't go into the details of why this formula has to be like that, except to say that it has to be actually verified experimentally by taking many measurements of the force, the field strength, current, and the length of the wire, trying out different values and checking with many measurements before it was confirmed that this is the correct formula.